Hi guys, Mr. Palmer here. I'm back with our review of conservation of energy, part 3. This is going to involve real conservation of energy problems, and we're looking at calculating our total energy. So we're looking at problems 6 and 7 here. The first one is a student on a skateboard that's going to be rolling down a hill. The two types of energy that are going to be involved in this problem are going to be gravitational potential and kinetic. So the student is going to be standing on a skateboard. It's going to be at the top of the hill. The problem is asking us, this is my terrible drawing of a student on a skateboard. It's asking us to calculate the height of the hill based upon some information about velocity at the bottom. So initially the student is at the top of the hill with 0 velocity. They're going down a frictionless hill, and it tells us that at the bottom the student is going 22 meters per second. That's up in our problem. And we're not giving any other information. So we're not given a mass, we're not given the height, so we're going to have to go and figure this out. Now we always know that if you don't give a mass, that's a good sign that it's not necessary or it's going to drop out. And your two choices are either keep it in as an m and it's going to cancel somewhere down the road, or put in a 1. If you put in a 1 and we just make up that number, it's not going to affect our results, and eventually it's going to drop out along the way. So let's think about this conceptually. At the top of the hill, the student has some total amount of energy, and that's going to be equal to the gravitational potential plus the kinetic. We've already said, right, if he's not moving at the top of the hill, this kinetic energy is 0. And so the gravitational and total energy are going to be equal. At the bottom of the hill, still the total energy is going to be equal to gravitational energy, right? EPG plus kinetic. But at the bottom of the hill, now we're down at 0 height. And so if you have 0 height, the gravitational is now going to be 0. And the total energy is going to be equal to just the kinetic energy. So what's really happening is that the gravitational potential energy at the top of the hill is going to be converted into the kinetic energy at the bottom of the hill. And it tells us that this is frictionless, so we know that there's going to be no energy lost to friction. So whatever energy you had at the top is going to be the same energy it has at the bottom. So we can go in, calculate what's that gravitational potential energy at the top of the hill. That's mgh. If we go to calculate the kinetic energy at the bottom, that's going to be 1/2 mv squared. Now if you don't know the mass, you could just substitute in a 1 here, right, and put that in. Or if you notice, we can set these two equal to each other because we know that they have to be equal because of conservation of energy. Energy is going to be conserved. Whatever I have at the top is what I'm going to have at the bottom. So if I say mgh is equal to 1/2 mv squared, we're saying that the gravitational potential energy at the top is equal to the kinetic energy that we have at the bottom, which is this one here. You can see in the problem that the masses are going to drop out. Whatever number that is isn't going to be necessary. We don't need it. Now, we know g is 9.8. That's not going to change. We're looking for the height. It's equal to 1/2 the mass, which we just dropped out, times the velocity squared, and the velocity was given to us. That was 22 meters per second, but we've got to square that. Again, it's 1/2 mv squared, and you're solving for the height. What are you going to wind up with? 24.69 meters is the height of our hill. Now, some of my students noticed that they did this with kinematic equations, and they just kind of said, hey, well, what would happen if something just accelerated down at 9.8 meters per second squared? So what if we did this and the guy just fell off the side of the hill instead of gliding down a frictionless surface? Well, if you do that calculation, you're going to see that you wind up with the exact same velocity, 22 meters per second, when you hit the bottom if you're falling from a height of 24.69 meters. And that's really just using the conservation of energy. We're looking at that motion from a different perspective. Number 7 is a slightly different take on this. We're now involving the spring energy, and this is asking us about a spring. we're trying to find the spring constant of a spring used to launch a ball. So let's get a spring. We're going to be launching a ball up into the air. Now at the bottom, we're going to be storing energy in the spring, EPS, 1/2 kx squared. And it says it's going to be used to launch this ball 5 meters into the air. So we're looking for the spring constant K. It's giving us a mass of the ball as 2 kilograms. It says the ball is being launched 5 meters. That's 5 meters high. That's this direction. H is 5 meters. And if that's the maximum height, we know it's going to come to a stop, right? It's not going to have kinetic up here. It's going to all be gravitational. And it gives us the compression of the spring as 0.65. Again, this is a conservation of energy problem. So down here at the bottom, when the spring is compressed, our total energy is EPS plus EPG. We're not even looking at kinetic energy, right? The kinetic energy is going to be 0 before this thing is moving, right? That's going to be 0. Gravitational, we're saying, is 0 at the bottom. So our total energy is equal to the spring. When we get to the top, our E total is still going to be the same thing. EPS plus EPG plus EK. And when we get to the top, the kinetic energy is going to be 0 because it's going to come to a stop at its maximum height. The spring energy is going to be 0 because the spring is no longer compressed. And gravitational is now going to be equal to the total. So just like in the last problem, we're having spring potential energy be converted into a different form. In this case, it's gravitational potential energy. So we're going to be able to set these equal. So let's take our spring energy, which is 1/2 kx squared, right? This is our EPS. That's going to be equal to our gravitational potential energy at the top, EPG, which we know is mgh. So now all we need to do is substitute in our values. 1/2 times K, that's what we're looking for, times the compression, which is 0.65, and that needs to be squared, is equal to the gravitational, the mass, which is 2 kilograms, times 9.8, times the height, which is 5. Solving this one, we're going to come out with a K equal to 463.9 newtons per meter. And again, we're setting these equal because the spring energy at the bottom here, that stored energy, is turning into stored gravitational potential energy at the top. So conservation energy tells us it's okay to set those two equal. All right, and we'll be back with another one about conservation of energy.